Okay, we have two logarithmic equations to solve. Take the first one. We have a sum of two logs at the same base. That's going to give us the log of the product. That's one of your rules. Okay. I think everybody did pretty well on the assignments. Expect even though those maybe something missed the assignment. We can expand this. We get the log of this equals 4. So we get the fourth equals x squared plus x minus 2. That's x squared plus x minus 2 equals 16. Now let's make sure I haven't made a mistake here, because it doesn't necessarily agree with some of what I saw, even though it looked like people were doing the right thing. Anybody say anything wrong with what I've done there? Because I've made a lot of mistakes this morning. Wrote down some certain things. Anyhow, if this is correct, 2 to the 4th is certainly 16. We got 2x minus x, and it gives us x. Yeah. Could be somebody didn't write my handwriting down right. Anyhow, there's the equation. That is then x squared plus x minus 18 equals 0. And I don't think you're going to be successful trying to factor this. There's no two factors of 18 that you can combine to get a 1 in front of the x. I mean, there are, but you're not going to find them. It's likely by trial and error. It's very likely that this is I've written it down here, but it's straightforward. You just plug the numbers into the quadratic formula. Okay. And check to make sure that makes sense. Okay, the square root of 73, it's between 8 and 9 because 8 squared is 64, 9 squared is 81. So that's going to be roughly 8.5 divided by 2, which is about 4 1/4, 4 1/4. Plus a negative 1/2, which is about 3 3/4. And you plug that back in and see if it works. Okay. And the second equation. There are two equally efficient ways to solve this. One is x minus 4 squared is 8. This is all straightforward. Multiply by 2 means you're going to take the square of whatever's in the argument of the log. We get this. We change it to exponential form. And I like to solve this because I'm saying x minus 4 equals plus or minus the square root of 8. This up x squared is 8. What do you square to get 8? square root of 8 or negative square root of 8. So the x equals 4 plus or minus the square root of 8. And the square root of 8 is 2 square root of 2. The other way you can solve it. You can divide both sides by 2. And then you get x minus 4 equals 2 to the 3 halves. Which gives you x equals 4 plus or minus 2 to the 3 halves. If you understand your laws of exponents, it's not plus. It's not a plus or minus, it's 4 plus. And you get 4 plus 2 times the square root of 2. That's what 2 to the 3 halves is. Notice that you don't get the minus sign. Okay? So there's something wrong with that minus sign. Anytime you get a plus or minus solution, make sure your solution makes sense. Okay? If x equals 4 minus the square root of 2 over 2, then x minus 4 is going to be negative square root of 2 over 2, right? Okay? Can't take the log of a negative. Okay? A log can be negative. You can't take the log of a negative. Log is inverse to the exponential function. Exponential can never be 0. And exponential can never be negative. Okay? That means you can't do the log of the negative. You might think about that. A little bit so, but if you want to thoroughly understand this, it's a good idea to think about that. I'm not going to write it down. I'm not going to test you. Okay? So we have a discrepancy. That works. But hard to read that, maybe. Sure, we can get a piece of red chocolate, nice. But I'm saying, if x is 4 minus 2 square root of 2, you plug that in, and then you're going to get the log base 2 log that I didn't even bother writing. But leads to log base 2 of negative 2 square root of 2. Okay? You don't believe that? Replace x by 4 minus square root of 2 over 2. And see that you get this. And that's undefined. Can't do the log of negative. Graph from the log base 2 function looks like this. The domain consists only of x values that are greater than 0. And that's because, of course, the exponential function, which is its inverse, can never be 0 and can never be negative. This will never reach 0, then when you switch coordinates, never reach zero on this side. Okay? If you're familiar with that manipulation of the graph, that's pretty convincing. Okay? And this kind of leads us right into the next topic. Okay? So there's a little bit of method to my madness. Maybe it's madness to my method. I'm not sure which. And today I really am not. But let's move on and talk about graphs of logarithmic functions. Okay? Because what I'm talking about here is a property of the graph of a logarithmic function. And the assignment of graphs of a logarithmic function is really pretty short. There are only 4 problems, and one of them is probably impossible. I'd be impressed if anybody can solve it. Okay. But I put it in there. Every once in a while, I like to give you a pretty good challenge. I mean, they give you a method. If you can execute the method, you get the solution. Might have the trouble, though. You know, I'm not sure everything I just said was showing on the screen. I thought I had this thing set up. I might have kicked this down or something like that. Let's make sure those last few comments. More or less visible. Okay. Again, I was talking about the fact that the minus there gives you a non-solution. Okay. And anytime you do a plus or minus or root thing, like with the quadratic formula or anything, you really want to check your solution to make sure that you don't get a solution that doesn't work in the original equation. Okay. Quadratic function, quadratic equation, it doesn't really care. But you got to make sure your solutions work, which is another good reason to check. Okay, so and you can check this one in your head, because again, if you plug in 4 minus 2 square root of 2 here, you're going to get a negative 2 square root of 2 inside the log. Because of the way the log graph never goes past the x-axis to the left, you're not going to get the value. This number is not in the domain of the log function. Okay. And again, and that leads us to discussion of graphs and logarithmic functions. So first of all, and I'm going to talk mostly about the log base 2 graph, but all these properties apply to any logarithm. It's just base 2 graph is the easiest one to construct. It doesn't go crazy off. It just, you know, if you try to do a 10 to the x graph, pretty soon you got numbers like 1 on the same graph with numbers like 100. Okay, y values of 1 and y values of 100. And it doesn't even get into the negative values where we get a 10 to 100. Scale gets ridiculous. Okay. So with the exponential function, remember, you can take your exponential function, reflect it, y equals x line, and what we're doing is the inverse of the exponential function. What's an inverse do? You know, if you don't have this somewhere prominent in your notes where you're going to see it when you review, you probably ought to make yourself a note to put it in your notes. The inverse function swaps x and y. You might want to also note that then you got to be careful about domains and ranges. Okay. If you have a one-to-one function, you don't have to worry. It's not a one-to-one function. You got to choose a branch. You've seen all that. But just reminding you. Okay. Yeah, okay, here's your y equals x line. You swap the x and the y, and you're going to end up with a graph that looks like this. It's a perfect reflection through the y equals x line. Okay. So this then is y equals 2 to the x. This is y equals log base 2 of x. And of course, you can start with a table and swap the columns in your table, and you'll end up with 2 graphs that look like this. Okay? We've already done that exercise. That should be very familiar to you. And I think on the midterm test, people did fairly well with swapping the X and the Y and get the graph and stuff like that. That was a midterm. Maybe not. Anyhow, I've seen people do this. Okay, in the whole and elsewhere. So I think you've got it. So anyhow, let's observe. Log 2 of X to take any value. I'm going to say, I started to say we can calculate, we really can't. Let me phrase this a different way. I mean, your calculator will give you a value. Okay, log base 2 of X will take any value. Because 2 to the X has a value for every X. That is, for any X, you get a Y. The Y equals 2 to the X function, right? If you switch X and Y, okay, that means for any value of the log function, there's an X that gives you that value. Okay. There's a Y here for every X, so there's an X here for every Y. That's what it comes down to. And you can see that from the graph. If you know how to construct the graph, you know that it's going to be true. Has a value for any X greater than 0. Okay. It's undefined if X is less than 0, and that reason comes down to because the exponential function can never be less than 0. And again, I'm not on space. Let's see if I That's because 2 to the X is always greater than 0. Okay. That means the Y for 2 to the X always has to be greater than 0. So the X for the log base 2 has to always be greater than or equal to 0. Okay. Since all these Y's are greater than or equal to 0 for this function, all the X's for this one have to be greater than or equal to 0. Okay. That's a greater than, just greater than, is greater than equal to 1. All Y's are greater than 0. All X's are greater than 0. Okay. And I guess I could say any Y greater than 0 occurs in this function Any x greater than 0 occurs for this function. We could also say abbreviated form, any x is possible for this function. So any y can't really help it, says possible. Any y is possible for this function. We conclude in mathematical language that the domain of y equals 2 to the x is the interval negative infinity to infinity. So it's all possible x values. The range is 0 infinity. Y equals log base 2 of x. What's the domain? 0 infinity. What's the range? Negative infinity, infinity. This says exactly the same thing I said here. I've just said it in many different ways. So we want to understand this. Once we understand it, then we can answer questions like this. What's the domain of brains not working? Leave stuff out. What's the domain of y equals log base 2 of x plus 7? Okay. Now I've asked, what numbers can you not put in to a log base 2? Well, doesn't everything that I've said here tell you you can't put 0 or negative number in? That this number has to be positive? Better way to write this. A log function, and it doesn't have to be a log to the base 2 function, any log function. Only operate on positive numbers. Now, at this point, the light bulb should go off. And again, I'm not requiring this. But a light bulb should go off, and you should say, ah, there's something I really ought to put in my review notes. That makes sense? Now, your light bulbs still have to learn when to go off and when not to. I mean, mine are still learning after 100 years, trying to understand general relativity. Okay, at least at a solid intermediate level. Okay. I understand all the math, but I think it's pretty neat stuff. Okay. A log function can only operate on positive numbers. Okay. As I keep rereading this book on general relativity, every time I reread it, I say, dang, I should have noted that. I should have put a star next to that. I didn't notice it. Okay. So it's a lifetime task learning what to annotate, learning what you're going to need to understand, bare minimum of what you need to understand to put it all together. Okay. And that's really where you're trying to go. Okay, so a log function can only operate on positive numbers. That's a biggie. Look, that's what I do in the margins of my book. Something's really important. Pretty soon I'll have every line of the book start. Great book. Okay, log function can only operate on positive numbers. So x plus 7 better doggone well be positive. You don't need to put the doggone well be positive in your review notes. Okay? It should be obvious if this only operates in positive numbers, the x plus 7's got to be greater than 0. Therefore, x has to be greater than -7, right? Well, so the domain of log of x plus 7 is -7 infinity. Now I just put down log. I didn't put a base there, did I? Well, since log means base 10 log, I'm going to say log to the base b. Still works. Okay. And any exponential function, as you should know, because you've done multiple choice problems that showed you all the possible range of graphs you have for exponential functions, you know that they can all go like this. They can be steeper, they can be less steep, or they can be backwards. Okay. That'd be like a negative value of your base, like one, not a negative, a fractional value of your base, like 1/2 to the x would be reflected through the x-axis, through the y-axis of the 2 to the x function. Okay. And if you don't understand that, well, you ought to scan it. Try to bring it together a little better. You've got limited time, so just figure out how to make your time work for you. All right. Every one of those functions is above the x-axis. So every exponential function is above the x-axis. So every logarithmic function is to the right of the x-axis, to the right of the y-axis. I'll get it right eventually. Yeah, these are all above the x-axis. These are all to the right of the y-axis, right? Okay. We can also see what the domain is, because if we graph y equals 2 to the x function, graph looks like this. here is x equals 1, right? I'm sorry, here's x equals 0. Something's not working here. This graph log base 2 of x. I put 2 to the x up here because I wasn't thinking. Okay, because my hand wants to write just whatever happens to occur to me, and my brain wasn't involved. Okay, y equals log base 2 of x. There's log base 2 of x function. And this is where x equals 1. And I was trying to plug that into 2 to the x, and I wasn't getting 0. I said, well, I can't get 0. Which tipped me off to the fact that I'd done something really stupid. Okay? Anytime you're doing or learning mathematics, be prepared to do something really stupid and hope you notice. Okay? Okay. So, anyhow, okay. I'm bored with it now. Here's x equals 1. Okay. So, where's the graph of y equals? R base 2 of x plus 7. Okay, well, I posed the question, how does this graph correspond to this graph? Well, if this is f of x, then certainly could say f of x equals log base 2 of x, right? How does that correspond to the graph of f of x minus h? You should know perfectly well from everything we did in extensive detail with shifting rectangles and graphs, toolkit graphs within rectangles. And that's something that's not going to go away. That's going to be in the file. It's going to count a lot. Okay. We want to try to put it together into a big picture that you carry away with you instead of forgetting it. Okay. Anyhow, how does this graph compare to this? Well, this graph is shifted h units horizontally from this graph. Okay. Graph of a f of x minus h plus k is vertically stretched by factor a, reflected also if a is negative. Okay. Then shifted h units, whether h is positive or negative this way or this way. And then it goes k units vertically, whether k is positive or negative. You know what I'm doing there? Put this to music and use my natural rhythm. I could probably make a TikTok video that goes so viral that we could pay students to come here and pay their tuition. Okay? Maybe I'll do that this afternoon. We'll see. Okay. As I said, just relieve the tension. Okay. Where are we? Trying to relate the graph of log base 2 of x, the graph of log base 2 of x plus 7, right? How does graph of f of x correspond to graph of x minus h? That's a horizontal shift of h units. What's h for this? Okay, so this is if f of x is log base 2 of x, f of x plus 7 is log base 2 of x plus 7, right? Now, how is the graph of f of x plus 7 related to the graph of f of x? It shifted 7 units to the left. This is x minus h for h equals negative 7. Okay? Make sure you really understand that, because I'm going to continue emphasizing it throughout the end of the course. Well, that means we've got to shift this graph 7 units to the left. How far are 7 units? Well, there's 1 unit. So we go 2, 3, 4, 5, 6, 7 units left. 1, 2, 3, 4, 5, 6, 7. Yep. So here's going to be our vertical axis. No, sorry. Yeah, we got to go 1 more unit because I'm going from this line. Okay. 1, 2, 3, 4, 5, 6, 7. Here's our vertical asymptote. Why is this vertical asymptote? So this is the line x equals -7. Vertical asymptote here. Is x equals 0. This should not be confusing to you because I've been having you write x equals when you do your subdivisions to construct your graphs. Okay, it takes that much repetition to get people to understand what x equals -7 means. Okay, and I mean I had trouble. It's so obvious. Why would anybody even talk about this? Somehow it just didn't seem important to me. Okay, I'm emphasizing it's important. It didn't take me long to figure it out, but still, I understand how it could be a little difficult to do this. Okay. There's your vertical asymptote. Everything else shifts over, so it's going to have the same shape. So it's going to go through the x-axis here. And by the time it goes over a couple of units, it's going to be this high. So it's going to 3 more units up here. So it's going to kind of look like this. That should have about the same shape as this. I just find they look, you get the idea. Does that make sense? Well, what are the x values that work for this function? Anything to the right of the asymptote, right? Meaning anything where x is greater than -7, which is, of course, the domain that we found symbolically. And, oh, phooey. It's the strongest F word I'm allowed to use here. Okay. Doggone it. I wish I'd remembered to record. Because this is really a big deal. Okay, well, it's not going to emerge as well as it might have, but I've got to say it on spring. Okay. I think we've established the domain and range of the x plus 7 function here. Then we ask, how does the graph of log base 2 of x correspond to the graph of log base 2 of x plus 7? People have trouble processing that, okay? And that's not surprising. This is not trivially easy stuff, but it's accessible. You can learn it. Okay? You can process it. You're smart enough. Everybody's demonstrated that. So I've got the graph of y equals log base 2 of x. How do I get the graph of log base 2 of x plus 7? Should be obvious, and I had to kind of correlate it. I went and said, how does the graph of f of x correspond to the graph of f of x minus h? Okay. Still did get an answer and did get a lot of looks of recognition. I think some of you kind of understood, knew you just tried to say. Okay. This is a horizontal shift of H units. And I said, the whole A f of x minus H plus K thing isn't gonna go away. Okay. It's how you build functions out of the toolkit functions. Okay, that and composites. I'm not asking you to construct graph of composites, but you've seen it in open math. Okay, that's a little more of a challenge. I said, well, okay, if you got A f of x minus H plus K, the x being replaced by x minus H, and please nobody play music because you know it's going to happen. It's going to move you this way or this way, right? Just like this. Okay. A vertically stretches graph and maybe reverses it. Okay. And K raises it or lowers it. So right there we have dance moves. You know, this, and this. Okay. Put that to rhythm. I probably won't have time to do that this afternoon. Put it on TikTok, however you do that. I never even looked at TikTok. Sometimes one of those videos does intrude on my browsing. Don't spend a lot of time looking for this stuff. Got to start making mathematics videos. By the time this afternoon, I could make a dance video. It would go viral and make everybody takes the courses here rich. Okay? Wouldn't that be great? But you know what? I love what you do. Okay? Because I don't want to become famous. I just like my semi-anonymous life. Be a pain. Okay. So anyhow, what do we do? Take this graph and shift it 7 units to the left. That's this one, right? Well, here's a unit because this is the line x equals 1, and here's your y-axis. So we come 1, 2, 3, 4, 5, 6, 7 units to the left. Y-axis, the line x equals 0 is your vertical asymptote. That's the line x equals -7. It shifts from 0 to -7 because x becomes 7 less. To do the graph of f of x plus 7. Okay? And then we just construct the graph and we do it real carefully. So it doesn't look that great. It looks kind of grotesque, but there it is. Okay. Now, as I said, this whole thing transformations. They have x plus h, x minus h plus k thing, toolkit functions and constructions and rectangles and stuff is never going away in this course. To be on the final, it's going to be important. We want to make sure that we relate that whole model to these symbols. Okay, well, now, so what's the domain of this function? Well, it's a set of all possible x values, right? You know, x values stop just short of this vertical line, just like they do over here. So just like the domain of this one consists of all values of x greater than 0, domain of this one has to consist of all values of x greater than -7, which confirms what we did analytically to find the domain. Now, since I forgot to record, I've said all of that twice, but it's worth saying twice. Okay? Everything except the dance moves was worth seeing twice. Okay? Okay, now is a little bit of diversion. It's not really diversion. It leads us into the next big topic. Okay. We looked at a kind of an oscillating system. It's not a pendulum, but you can imagine a pendulum, okay? And eventually it wears down and takes a long time. There's a pendulum, well, it's attached to something, so I'm not gonna get it started. If I get that thing started, it's about this long, pull it back a little bit, let it go. It's gonna go for close to an hour before it stops. Okay, the system we have here would have gone for maybe 5 minutes. We're looking at how far it oscillates. And the graph looks like this. That's about what you'd expect. If it's oscillating a whole lot, it has a whole lot of distance to lose. Okay, now what's really going on has to do with air resistance and friction and stuff like that. I don't want to talk about this class, but you can kind of think of it intuitively. The further it's oscillating, the more it's going to lose for oscillation. What's oscillating just a little bit, it doesn't have much to lose, but it still keeps going for a long time, so it must not be losing much. So the graph might look kind of like this, and I hope that is visible. There's got to be a way. Zoom puts its anyhow, I'm sure I can see it there. Okay. Looks like this. Well, then we went to Excel and saw that, as I said, there's no reason I would have expected what we were observing to be actually exponential. We went to Excel and we did a trend line, and the exponential trend line kind of looked like this. It was too high over here and too low over here. Okay, wasn't a real good model, and I didn't expect it to be a real good model. And I hadn't analyzed it any further. It'd be a big differential equation. It takes time to mess with it. Specialists, it's probably not solvable. I like to go to numerical solutions. Would have been a mess. Anyhow, okay. Well, one thing I showed you was this. The other thing I showed you is if I try to add a trend line, what are the options for a trend line? Exponential, logarithmic, power function, polynomial, or linear. Not in that order. Okay. What have we studied in this course? Linear, power functions, including quadratic, power, well, power functions. That's just your x squared or x to the fourth or whatever. And that's what your polynomial graphs approach to infinity. And the power functions all look like a cubic function or a squaring function. With the higher power, they get flatter towards the middle and they get steeper at the ends. If you know that, that's pretty good. Okay. Now, if you can manipulate the symbols to where you can actually use that, that's even better. Okay, now my point is, this is Excel. What's Excel use? It uses exactly the functions we're studying in this course. Okay. And Excel is used by scientists, engineers, business people, psychologists, criminals. I'm sure a lot of criminals use it too, but don't go that route, please, because I think you'd be really good at it. Okay. Yeah, you'll have the potential to be good at whatever you do. Okay. Unless you want to try to maybe be a theoretical physicist, which one person in 10,000 could do. Okay. For a brain surgeon, you got to be almost as coordinated as I am to do that. Okay. All right. Well, that kind of leads us into the next topic, I think, if I remember what the next topic is. Okay, I think we've done the turkey model. But we're going to do it again because Thanksgiving is 3 weeks from today. Okay. As I say, everybody's got their turkey nice and fat, getting ready to harvest the thing, cook it for Thanksgiving, right? Well, you look at me like I'm crazy, you know that. So how many we have turkey at Thanksgiving? Yeah, all of it. Okay. Well, how do you get turkey if you're not raising your own? You trust these corporations to give you an edible turkey? Well, actually, they do a pretty darn good job. So yeah, I trust them. Okay. There are a lot of things I don't trust them, but that's they're pretty good at that. Okay. Turkey temperature is 140 when T equals 20. It's 120 when T equals 60. The graph which temperature looks like this. First of all, capital T here is room temperature. Little t is time in minutes. Temperature is in degrees Fahrenheit. Okay. Now you need this room temperature on your graph. Okay. Because what's happening to the temperature of the turkey? It's not going to go below room temperature. Okay. If it's in the room, it's not going to go below the ambient temperature if you have a constant ambient temperature. And theoretically, it's never going to reach the ambient temperature. It'll go halfway, then it'll go halfway, then it'll go halfway, then it'll go halfway. It'll keep going halfway forever. Theoretically. Eventually you get down to the last energy of the last quantum, and you're talking about probabilities that that last quantum is going to engage. Okay. And you don't know what I mean by that. So in reality, any measurement you can make, it will reach zero, but not really. Okay. There's always quantum probabilities preventing from reaching zero. They're not relevant because the temperature of the room is going to fluctuate a little bit anyhow. But okay, so our temperature, let's say T equals 60 here, and T equals 20 here. Then what you have is T equals 140 here, T equals 120 maybe here. What's your room temperature? Let's assume your room temperature is 70. Okay. So those points kind of make sense. The rate at which the turkey temperature approaches room temperature is pretty much proportional to how far it is above the room temperature. The graph is going to look like this. Our model is T equals A B to the T plus 70, because this exponential function has an asymptote here at 70, so it's been vertically shifted 70 units, right? Okay, it's not a basic exponential function, it's a basic exponential function, shifted up 70 units, because the asymptote of a decreasing exponential function is the t-axis. To get the asymptote up to t equals 70, you have to raise it 70 units. Well, there's your model. What do? Oh, just real quickly. So temperature is 140. Right there you have two equations. And we've talked previously about how you solve these equations. Okay. So you could quickly solve them. You subtract 70 from both sides, you get 70 equals AB to the 20. You get 50 equals AB to the 60. So this is now your equation 1, your equation 2. So that equation 1, A equals 70 over B to the 20th. Equation 2, then 50 equals A B to the 60th. The A is 70 over B squared, B to the 20th, sorry, times B to the 60th. So 50 equals 70 B to the 40th. B to the 40th equals 50 over 70. So B equals 50 over 70 raised to the 140th, which you can punch in your calculator, and you got B. Then you plug that into either equation and solve for A. You can even plug it back into here and solve for A. But you want to check on both equations. You'll be out of time, so we can't do that. But you understand that once you put your data into a reasonable model, you got something that's really pretty easy to solve if you understand your rules for exponents. Make sure you understand your rules for exponents. Okay. There's a step here that you take the 140th power of both sides, or the 40th root of both sides. It's an equivalent thing. Okay. And that's something you're supposed to know when you come in. That at this stage, pre-calculus course, people still shaky on it. We'll talk about it next time after you've encountered it in these problems. Okay. There are quite a few problems in this assignment. There are 2 assignments over the weekend. One of them is short, just on the graphs and the domains and stuff like that, like we talked about. And the other one is exponential models. Okay. Sometimes they give you the model, sometimes you got to find the model. And there are quite a few problems in that one because this is really what exponential functions are all about. After this, we don't do that much more with functions, except some review. And we get into simultaneous equations and stuff. So you might also want to review what we did on the intersection of 2 lines using elimination. It's a little bit of advice. You'll understand it better if you at least glance over it before class.